Yes. So, good morning, everyone, and welcome to today's webinar on axle box acceleration measurements for railway condition monitoring. This event is brought to you by the EU and Shift to Rail funded project into Track 3. My name is Mats Sibon, communication consultant at Spinverse, supporting the coordinators, Trafikverket, the Swedish Transport Administration. You as audience will not be able to use cameras or microphone in this webinar. However, the chat works, and so does the reaction button. So please use the reaction buttons. That's fun. And when you ask questions in the chat, we will have a discussion part by the end where you will hopefully get your questions answered. Today, joining me is Pernilla Edlund, Project Manager at Swedish Transport Administration. Pernilla, would you like to share a few words?
Thank you very much. Yes, I would like to. We can move on to the next slide, please. I am the coordinator with the Intertrack 3 project. We started out in 2020 and we are finishing now in 2023. So we have a few months left to go and we're approaching the end with some really nice results and some really nice research. That is, this webinar series is a part of that. We want to share this with you and to tell the world what we have done because it's really interesting. So can we move on? Briefly, the Intertrack 3 project consists of 26 partners in 11 countries in Europe. It's a EU project, European Union project, and we have all sorts of participants, meaning that we have infrastructure managers in the project. We also have the people taking products forward, and we also have universities and research institutions, which give us kind of broad perspective on how to tackle the issues in the railway research part. And we try to do that as much as we can. And we also have other projects preceding us, and we can look at them on the next slide. Because Intertrack 3 builds on the work in Intertrack 2, 1 and Interrail, and before that other projects as well. And the pictures below are only merely an illustration as how we have progressed into higher TRL levels. And Intertrack 3 has the aim of having as many TRL 7 products as possible. And we are reaching that goal pretty well. We have over 30 demonstrators showing TRL 7, which is that we demonstrate it in an operational environment, which we do in all sorts of aspects of this. We can take the final slide, please. Only showing a few of the things that we are. These are just a snapshot of a few things that we have taken forward and which will continue in projects after this and will be continued to work on. It will move on to other projects as well and other research. Some are very close to industrialization and they will move on in that direction, while other things need more research, more inventions and innovations to function properly. But this is towards the end of the Intertrack 3 project, so please hear what we have to say on the axle box part. Thank you.
Yes, thank you, Pernilla. Now I'd like to welcome Arjen Soterman from Prorail to give us an introduction of the axle box acceleration and to lead the webinar and the discussions from now on. Welcome, Arjen.
Thank you. Yes, Arjen Soterman indeed from the Prorail Innovation Department. We are a member of I was looking to the slides, but now to you. The Intertrack projects we started first was Intertrack 2 and then also Intertrack 3. So we were not there from the very start. But I'm a big fan of what you just showed. I think also on dissemination and the innovations that we do. It's really for all to check out the website of Into Track 3. It's really good. And I think today is also an example on Excelbox accelerometers. We want to really present to you what we've done. The history that we do research on it goes back many years already, together with, for instance, Delft University of Technology has been leading it in the Netherlands for many years. And now we also brought in this, what we have developed with ABA into Track 3. And yes, certainly hope to, actually are continuing that in the EU Rail project. So we will show what is the state of the art at this moment. There will be presentations from TU Delft, and also afterwards we also find it very important to have some application from practice and some feedback from the market. So that's why we approached Asset Rail as a user in the Netherlands. I'll also surprise myself, Mart, by what you will present, and I think that's good for us researchers to really know how things are going in practice. And also from DB, Burkhard Riepke will have a short presentation, and then we can have questions. Also on the chat you can have post questions, and we might hopefully be able to go through them all. So ABA, it's a tool. It's known for, of course, track irregularities and incident management in that area, but also we sophisticated the technology, combining it with AR filtering and all sorts of methods that we get the precise information on defects in the rail also, but hopefully also further into the structure. And yeah, it's one technique that's quite established to use it for that, but the new methods of analysis and data analytics provide us new grounds to go further. And I don't exclude that this is the only technique that we will apply. So also in EU Rail, we will go on and move on with other techniques in this area. So we have to remember it's a tool to get our maintenance better and our prediction better. And I think we have made some nice results into Track 3 particularly, and where we also showed a very good example of cross-border European cooperation, actually, where we brought the technique into quite an extreme area with also climatic, which is Lapland. But I understood it was very nice also for testing. I think it was at the time that there was almost daylights all day. So this is a perfect example which we can't achieve in the Netherlands. So it was really nice to go there. And before I give the word to Alfredo and Chen, who will presenting on this, what they've done in Into Track 3 specifically, I think there is a video to demonstrate. And Alfredo, you will start it. I hope the sound's working.
Yes, so I am sharing now the video. Yes, I will put play.
I don't hear sound yet.
No, we are in Sweden. Welcome to Sweden.
We are in the line between Luleå and Narva in the demonstration campaign for detection of road contact fatigue for the project Into Track 3. It's a cooperation between Prorail, Trafikverket and TU Delft.
RCF is a quite widespread problem in worldwide, also in Europe railways. And the most effective way now is to detect at an early stage. Then preventive and corrective action can be taken as soon as possible. And one of the challenges is then to develop an early detection method. This is what we are now doing, and also doing demonstrated not only in the Netherlands but also outside.
I think to have this type of monitoring in service is really efficient for us in Trafikverket, because we can use this as decision making later on.
We're at the southern part of the iron ore line between Boden and Luleå, which is quite a trafficked line, both with passengers and the iron ore and the steel from the steel plants. It's a very used line, and so it's a good place to do tests and developments to use all over the rest of the network.
We are heading to Narvik in Norway. So on this train we have axle box acceleration measurement from the AVA measurements, especially from the frequency domain of the AVA signals. We could get different characteristics of the stiffness of different layers. So from these measurements and also the field validation campaigns for into track 3, we would hope to develop and validate the capability of AVA for track stiffness measurements.
So part of the research is also to have a better understanding on freight-dominated railway lines. And the more information we get about their behavior, the particular characteristics, then we can also then further extend the monitoring methodologies.
This one will grow, and we can measure it with the AVA system that we have seen. If we come back in a couple of months, we will see that the crack will, the spots will be bigger and bigger and bigger, and finally this rail will break. If you don't do anything, it will break.
All right, so we are now finalizing our demonstration campaign for detection of rolling contact fatigue. So we thank a lot the colleagues from Trafikverket that arranged everything and made this campaign happen. And we will see each other soon, I hope.
Yes, thanks for the video. So that's already an appetizer, I think, for your presentations. And yeah, I think this technology will have a lot to offer. We are, yeah, the TRL levels were shown in the first slides. I think we're at that level, so we have to do, of course, more. But we have some examples later on also of usage in the practice already of daily maintenance. So that this is, of course, where we want to aim for. And that's also in the next projects for EU Rail, the aim to really go to the application we only develop because we want to apply it in the end to make the railways better. So, and I think this is a very good example. So I want to give the word to Alfredo. I don't remember how much time you have, but maybe you know yourself to present, and then you give the word to Chen, correct?
Okay, thank you very much, Arjen. I will start sharing my screen, and I think I move this into presentation mode. Is it now visible for all of you?
Yes, and I also just like to add that the plan is that you should be finished by 10:20, but yeah, just so you know. Okay, otherwise you can do some more minutes.
Okay, I'll try. So welcome everyone. It's great to have a lot of participants today in this webinar. I'll be talking about axle block acceleration for railway condition monitoring. In the campaign for Into Track 3, we have a lot of colleagues involved. So from TU Delft, from Prorail, also Matthias Asplund from the Trafikverket, and also other colleagues that also supported during the demonstration campaign. So why the use of AVA? This is the situation in the Netherlands in a normal day. You can see that our tracks are super highly occupied, and any problem that will happen will affect a lot of people. And so, but what looks like a challenge is actually also an opportunity, because nowadays, all of those new trains that are arriving, they are already instrumented with smart sensors. So we can then see the opportunity that we can use the trains not to just transport people, but also to give us information about the condition of the railway tracks. And then whenever we need information in one region, we could activate the rolling stock that is passing by there, maybe not just with AVA, but also the video cameras, lasers, and so, and we can extract updated knowledge and almost in a continuous way to have updated information about the railway track. So this is the motivation then for us to work with monitoring systems that are on board. That is then ideally in passenger trains, to instrument them, so to collect all the information while on the run. And then here you can see a video of the CTO train of TU Delft that we use for research. And then we have then tested here different technologies in the Netherlands. You saw already the video about the campaign we did in Luleå. In this case, the CTO train was not taken to Sweden, but then the colleagues that they have the expertise on mounting the technology, they went to Sweden to install in a passenger train. So the basic principle of AVA is as follows: the wheel will pass over defects and it will fill it. So we investigate deviated dynamic responses by using the accelerometers at the axle boxes. Here you have different types of squats, some that goes for very light, moderate, with some cracks already developing, and then later some severe squats, where you also see here the extension of the running band. We also have squats that are originated due to certain locations, certain components, such as thermite weights. Here you can see two squats. In the measurement system, then we collect information from the vertical and longitudinal signals. And by using the physics of the problem, the modeling approaches that allow us to understand the track behavior, the AVA behavior at components, at defects, then we make use also for signal processing techniques to extract all this knowledge and to provide an information about the condition of the track. Not only the wheel pass over squats, but also corrugation, components such as insulated joints. So for all of them, then this system can also be information, additional information system about their condition. Here you see examples also that we have worked on, for instance, transition zones, insulated joints, crossings. Here we have frogs, and then the AVA can assess their condition, but also, for instance, here it can evaluate the quality of the maintenance work. So, for instance, in a nominal condition, you have a certain response energy level. Once it's degraded, this energy, of course, changes. But then after this frog got repaired, you can measure again, okay, what's the quality now of the repair operation? And in this case, the signals, the energy actually got increased. So you could also assess and make use of AVA to evaluate the maintenance work. Over here, you can see some examples of squats that were found in the Swedish railways. So the general, here let me explain a bit the general principle. So the AVA at moderate and severe squats, it will generate a certain response. Then when looking at the time frequency analysis, it shows us the frequencies that are activated. In this case, for a certain speed, here typically you have a low frequency band that it gets a bit dominant for severe defects. But then also, because the squats are a short events, a small, let's say, they have a small duration, they also excite higher frequencies. For light squats, the technology that the TU Delft we've been developing that also considers longitudinal signals. And then in this case, the smaller defects, then they will create even shorter time duration of excitation. In the case of early stage defects, then they appear once they are in a very early state and start to evolve, they're going to be appearing more and more frequently in the signals. And there's a moment when we see this light and some defects that are invisible defects that after every time the train's passing, it's reporting that there's an impact that then allow us to claim that the system can systematically detect them and monitor them because of the physical response. The technique then, why the detection of early defects or later defects? The thing is then, and why to do it continuously? The reason is that some small defects, they are candidates for effective grinding. That means that then with a certain depth of grinding, you can completely remove them for the rail surface. But then when the defects, they grow too much, then grinding won't be effective. Then you can apply grinding, but then the defect will appear again and again. Now for the case of severe defects, yeah, they got not removed by grinding, that can happen. Then the effective replacement is also important because you can know of first to guarantee safety, but also you can estimate in which maintenance campaign this defect could be replaced. So then you don't need to wait till this rail gets broken, but to optimize it and to maneuver a bit with the maintenance operation. In the detection, then this is a dynamic measurement, so we will have different speeds. And here, for example, we show you an example for wheel burns at 80 kilometers per hour. You'll see over here the responses. Now at 200 kilometers, same defects, they have a much higher excitation. So the faster the train, then the higher the energy of ABA. And then in the real life detection that you have variations of speed, the signatures then can be adapted based on their frequency and the wavelengths and the speed of the train. For Luleå and Narvik, we conducted a comprehensive measurement campaign. So as mentioned already in the video, this is mixed traffic. We mounted the sensors in the passenger train, but there's also iron ore trains, freight trains that are super heavy. And and this is more or less how it looked like the campaign that we did. I will show you later some other tests. So we were, let me show you here the campaign. So we did the 2 rounds between Luleå and Narvik. So some of the colleagues, they traveled with the van from Delft to Luleå. Took them like three days, I think. So then that was the installation. The train went from Luleå. We passed the polar circle, and then we arrived also to Kiruna, and we went further to Narvik. So we created then the RCF maps for the general detections, identifies severity of the defects at the different frequencies. And then we designed a validation campaign in 5 different locations in the Swedish part. So these are the 5 locations. They were all near Luleå. And then we went to first two of the locations, and then after with some preliminary analysis, then we went to the other location 3, 4, and 5. For validation, then we perform visual inspections for which we register the photos. We also, to verify that we are not missing defects, then we also did a GoPro video. In the locations, the geometric measurements were also conducted. And in some few defects, we did some 3D scans. So for the AVA part, these are some pictures of the installation. What we did for analysis was to analyze the wavelet responses of the signals. Then basically the train was passing over here, and then we detected the map of locations and defects. And then later we compare field test with the analysis. The key findings, and I think I'm on time yet. All of the squads that we observed in the 5 locations were detected with the AVA. The AVA also indicated the locations. I mean, the principle is that it detects locations with the higher impact excitation energy. That's part of the method, and they can be useful also for instance, the monitoring of welds and the effect of a small defect. Also, then for the detection of severe defects, this technique was run almost in real time. So as the colleague, Jurgen Hendricks, was on the train, he could provide us on the most, let's say, interesting locations to visit. So the new sensing technologies and systems, they allow an almost online processing, overcoming the problem of the big data set that we have to collect. So the more information we have about the field and matching what we observe in the field with the measurements, it increases the decision powers. It allows us to maneuver and to decide on the best maintenance strategies. So as a recommendation then from this study, the system will be even more powerful and it will help also the other measurement systems when integrated into existing rail asset management tools. That is because of the physical interpretability of ABA, but it will also help to other systems. Although ABA requires some advanced time frequency tools, then the signals are insightful, and they can be used and converted into KPIs that allows for simple indication for maintenance decision level, let's say at a higher level. So
Alfredo, excuse me,
yes.
Alfredo, is this your last slide? Because we are
Yes.
running out of time. Yeah, great.
Okay, thank you. So, and then as for the research on the rolling contact fatigue, validation of KPIs will be interesting, key performance indicators. Also to evaluate the work orders, for instance, the grinding clustering to decide where to grind, to evaluate the grinding techniques based on AVA information that could be of major interest. And also the refined positioning. So nowadays, the rolling stock will bring together the system so we can align it not just with the GPS, but also with the tachometers and train information that will allow then a much better positioning. So for instance, we install a GPS antenna, and then of course we know that in the tunnels this didn't work in terms of the positioning, although the responses and the signatures of the track got captured anyway, of course. So I acknowledge then to all the colleagues that support us, and just the next project we are working also for rail, in embedding also the AVA system with the other technologies such as laser Doppler spectrometers. So thank you very much for your attention. I think I was almost on time.
Yeah, we have to. So we introduce Chen for the next presentation. We are a bit after, so if you could keep it short, try and do that, please. Go ahead, Chen.
Yeah, thank you very much. Yeah, I'll be short. I'm now sharing my screen. Can you see my screen now?
Yes.
Okay. So as Pernilla and Arjen already mentioned, this is a continuation work of Into-Track 2. So using the ABA technique to evaluate railway track stiffness. So in Into-Track 2, we validate the technique in the lab. So the goal of Into-Track 3 is to further validate it in industrial relevant environments, which is at TRL level 5. I'll start my presentation with a short introduction of why we want to measure track stiffness. Because track stiffness, especially its variations in space, leads to increased wheel and rail force. Here there's a video showing there's a loosened fastening system, which I don't know if you could hear from the video. There's impact noise from it, and these increased wheel and rail forces would, if it's in the high frequency domain, could probably lead to defects on the rail surface, such as squats and corrugations. And if it's in the low frequency domain, it travels further down. It could lead to track geometry degradations, for example, especially at transition zones. So all of these would eventually result in increased maintenance costs. But the existing technologies of evaluating track stiffness, we have specialized measurement vehicles, but usually they only measure at a relatively low speed and can only excite the track at a relatively low frequencies. And for the in-service vehicles techniques, most of these techniques only measure the stiffness at a single layer. So they look at the supporting stiffness overall, and there's a lack of field validation. So the basic principle of measuring track stiffness is, I think this figure already you already saw in the presentation by Alfredo. So we look at the vehicle track as an integrated system, so the ABA can fill the underlying track properties, including track stiffness in particular. So each layer of these track components may result in different vibration characteristics in the ABA. So therefore, if these characteristics could be captured by ABA, it could be used to measure the dynamic properties or the stiffness of different track layers. But if we, but the problem is, how do we distinguish those kind of characteristics from the ABA? So if we look at the time domain signals, it really does not tell a lot about the dynamic characteristics. But if we transform it into a time frequency domain, we could see these the characteristics of these time frequency representation is also layered, and rightfully so, because the vehicle track dynamic interaction is a system that has high frequency vibrations at the top of the system and at low frequency vibrations at the lower part of the system. So if we could measure the characteristics, the dynamic characteristics from the ABA at different locations, we may be able to identify the stiffness variations based on these characteristics. And in this technique, we propose to use a local frequency feature. So we take basically we take a window of this time frequency representation and project it to the frequency space. And so the question now is how do we establish a relationship between these ABA features and the track stiffness at different layers? We actually used a vehicle track interaction model, so VTI model, to establish this relationship. We start with the parameter space. So here I show the KB is the ballast stiffness and KP is the real bed stiffness. So we sample from this parameter space to represent different conditions of the track, and we use that as an input to the VTI model. Then we can get the ABA features corresponding to different combinations of real pad ballast stiffness. So with that, we could build a discrete relationship. So for example, here the red dot would correspond to a red curve or the red features in the feature space, and this yellow dot would correspond to a this yellow feature in the feature space. And with all these, we could build a database actually with the input of the track stiffness and output of the ABA features. So based on this database, we could train data-driven models which establish a relationship between the ABA feature and the track stiffness. And all these modeling and training process could be performed offline, so that for online evaluations, once we have a feature measured, we could give it to the data-driven models, and it will give us an evaluation of the track stiffness. So it's relatively fast. So here I show how the validation of this method in a field test in the iron line in Sweden. So we choose a transition zone, so a bridge and a transition zone where we evaluate the stiffness variations in this transition zone. And we received great support from the Swedish Transport Administration for this field test. So I would like to acknowledge that. So more specifically, we're looking at the stiffness support at these 10 sleepers from the embankment to this bridge. And we instrumented a passenger wagon that travels frequently in this line with axle box accelerations. And we also conducted some hammer tests on this location, so that the results of the hammer test could be used as a validation of the evaluation by the ABA. But it is also important to, yep.
Can you end in 1 minute?
Yeah, I'll try.
Thank you.
So this is basically the test we've done. So the first step is to validate our models. So this is the validation of our model. The black line is the simulation, and the others are the measurements. So this is the hammer test result. It reflects some dynamic characteristics of the track. And this is the validation with the ABA features. So the red lines are the measurements, and the other two lines are the simulation results. And we can see also multiple characteristic frequencies that corresponds to different resonances of the system. So that could be used to distinguish the stiffness in different layers. Here I show you the results of the evaluation of the real path stiffness at the 10 sleepers. You can see the general trends are similar between the ABA and hammer tests. But if you look at the absolute values, what we could see is that the evaluation by the ABA is actually higher than the hammer test. This is because of the ABA is in the loaded condition, but hammer test was conducted in the unloaded condition. A similar trend for the ballast. So the stiffness evaluated by ABA is also larger than hammer test. And if we look at the structure variations, actually we could see that the support stiffness of ballast decreases in the transition zone towards bridge. And between this sleeper 6, 7, and 8, it's actually constant. But at sleeper 9 and 10, it increases again because there is still support here at the bridge. So here's a short summary of what I've presented. So the stiffness of each track layer was correlated to specific features in ABA signals, represented by a local frequency domain feature vector. So the technique was validated in operational line by comparing the stiffness evaluated using ABA from an in-service vehicle with that obtained from hammer tests. And in future, we would further demonstrate effectiveness and the application of this technique under different track operational conditions. And in practice, we would use that we would use frequent ABA measurements to gain better understanding of the track stiffness changes over time, to better inform the maintenance decisions. And thank you very much. And I think that's my presentation.
Thanks. Yes, we are. This was, I think, really informative and really hard to do it much briefer and very interesting to. So I think we didn't want to interrupt you, but now we are a bit late, I think, and we have now also the panel and some presentations from practice. So I see there's a lot of on the chat. There are questions, and I ask Alfredo and Chen, maybe Rolf and Zili, if you can best answer them already on the chat, so that everyone gets happy with the knowledge they ask for. If we don't answer it now, we'll answer it later, and we take as many as we can to the panel time that's left. But I want to ask DB and Asset Rail also to reflect briefly from the early market applications of EBA, and really it would be good if you could keep the 5 minutes. For the order, it doesn't matter to me. I don't know what was written, but maybe Mart can go first from Asset Rail. Is that okay?
Yeah, sure. No problem. I will keep it short. I have just a few slides, so we'll be okay. Let me see. Is it loading? Yeah, there it is. Yeah. So just short introduction of myself. I'm Mart Volkerts. I am head of asset management within Asset Rail. And maybe short on what is Asset Rail for who doesn't know this company. We are a maintenance contractor which performs performance-based maintenance contracts for Prorail. And performance-based maintenance means that we are we have the freedom to or let's say partly the freedom to decide which maintenance we need to perform to make sure that the track is in the best possible conditions and there aren't as less as possible delays for the passengers and for the freight trains. To make sure that we have as many delays as possible, we also decided back in 2017, after contact with Rolf and also Julian Hendrik from the TU Delft, that hey, it's interesting to do a test with ABA measurements. Well, in the last 6 years, we've done several, which gives us a lot of interesting information about the condition of the tracks. We also used the CTO train where the axle box meters are already on. And the insights that we gathered were on the one side very positive. So what we did, we used the different points that came out of the different defects that came out of the measurements. We analyzed them and we used a sort of clustering algorithm to decide, hey, where do we need to grind? Where do we need to mill? Where are severe defects and where are less severe defects? But we, at the end, we still decided to not use it for our decision making. And there are a few reasons for that. I've summarized them over here. The cost of and the measurements and also the corrective actions behind that are very high. And as a contractor, we always look at the costs. And what's also a big thing for us is, if we do the measurements and the analysis and the corrective actions, we're not sure if the defect is really gone. And that's because we can't, or from the measurement, we can't estimate the depth of the track. We can make an estimation, but we're not sure. So if we perform a milling exercise, we're not sure if everything is gone, and we still have to do an ultrasonic measurement to check, hey, is everything gone or is there something still there? And if there's something still there, then it's even less interesting to perform it like this. The last reason, there are also other ways to gather information on the defects. And maybe the most important one, and I haven't even written it down here, is that we as a contractor are responsible for the safety of the track. So it's quite difficult on, when are you going to rely on technology to make sure that the track is safe. So we have multiple things in place there, and a lot of people who are looking to the safety of the track. And I think that ABA in the future could help us to make sure that we can prevent stuff earlier than we're doing now. But at this point, mainly the cost aspect, and that we can't gather the information that we really need to decide on, are we going to perform maintenance, yes or no? That is what makes it for us that we're not using it right now in our decision making, but we use it to gather a clear view of, hey, what's the condition of a certain area, and what can we expect in the future. Is that short enough, Mats?
Yeah, I think if I answer it, this is good. But this definitely needs to move on to a question on the panel, because this is a good interaction between practice and researchers. So we're not ready. That's what we know. But maybe better for time reasons first also to ask Burkhard also for 5 minutes, and then we have the combined picture of practice, and we can have the interaction. But definitely we have to come back to your presentation, what you just presented. So if Burkhard is ready for only 5 minutes.
Okay, I will do my best.
Will you present, Burkhard, or should I do it?
No, I try. Normally you should see my screen.
Oh yeah. Yes.
Yeah. Okay. So before I start my short presentation, I want to make a short introduction about my person. My name is Burkhard Ripke, and I've been working at Deutsche Bahn for a long time, and have been dealing with the topic monitoring with ABA for more than 10 years. And I think we have a team at DB that is working at DB Netz. I'm just talking about DB Netz, at DB Netz, which is working on this topic, and we get new people working now, so we have more people to work on this, and this shows the attractive system. So we expect a lot of information from this. But the real challenge for me is now to tell about this interesting topic in 5 minutes. So I think hopefully I have only 2 slides in this case to reduce the time, but I think it is a really interesting topic. Okay, I have 2 parts in my presentation. One is to see what is the status quo at the moment. So if I look at today, we are operating nearly 10 trains. If you take into account working trains, we are installing now also monitoring technology. We have more than 10 trains. And the maximum speed is up to 300 kilometers per hour. This means we have also IC3 train equipped with monitoring technology, and we use all this train to monitor at the moment, I think 3,000 kilometers of the network each week. This is a lot of amount of data. I will come later on to this. And we plan the installation of more trains, up to 5 passenger trains. And then, as I mentioned before, in different working trains. This has a big advantage that DB Netz itself can operate this train and run exactly the tracks we are interested in. A typical installation is shown on the left side. On the right side, this is carried out in Automain. This is I just looked today. It's more than 10 years ago that we installed the monitoring technology in this locomotive, and it's still working. So ABA technology also on the freight train in a rough environment. The train is the locomotive is running from Rotterdam to the Dillinger Hut on part of the rail freight corridor 1, and it's really stable. It's really not a problem. It's more a problem of the locomotive if something breaks down. In principle, why is monitoring based on ABA so interesting? I think we heard about this. Alfredo talked a little bit about this. It's not an optical measurement. It's a dynamical measurement. So the data contains much more information than if you, for example, look for classical inspection method, which are optical. So this is really a big challenge and a big advantage of this measurement that maybe the vehicle track interaction is included in this data. As we start with this, we are just looking for meteorology. So we have to improve this measurement, and what we found out that the results for gathering the track geometry from the ABA are absolutely identical with the inspections results. You can see it on the right side. There are different runs. You see that there's high reproducibility, and the blue is that we have a comparison between inspection and the measurement with ABA. That means, in summary, a key finding is that monitoring with ABA is a valuable method that can supplement classical inspections and support asset management. If I look at the application we are working on and we are partly using, this is, for example, we are looking for track geometry monitoring, which bridge the gap between inspections and if you look in Germany for the standards, our maintenance, our inspection depends on the speed of the line, so not on the load on the line. And if I look at the rail freight corridor 1, for example, we have monitoring intervals of 6 to 12 months. It depends on the speed of the sections. So it's very good that our locomotive runs each week at least twice a time, and we look for this, and therefore we close the gap, and we can identify with this maintenance needs, and this is really good application for monitoring. The second is that we want to combine the maintenance of the track geometry and in the track and in switches and crossing to have a more efficient maintenance, and therefore we use, for example, also ABA for monitoring the transition geometry in switches and crossing. This is also is an application where we may be able within I'm4Rail, this is the newest project we are working on, that we can also make a prediction, not only to see this actual state or current state of the transition geometry, then also use it for the prediction. A new method, what we are doing since this year, is that we try to monitor the sustainability of maintenance measures. This means, especially if we have a rebuild of a track and we know there goes something wrong during this because we have bad weather condition or not enough time, or so, and we are using monitoring to look for the sustainability of the maintenance measure, whether it works or works not. Do we get problems? And if you look for the whole network, then we can also see the impact of different maybe building strategies or maintenance strategies, how this has an impact on the sustainability. What is really new and what we are doing at the moment, I think more in the manual way. So we are looking for more data analytics to make it automatically, is to detect the anomalies in the rail surface. I think this is very important because in our planning we want to make a root cause analysis and make a more efficient maintenance if it's possible to remove the root causes. And therefore we can see in the upper figure the different anomalies we can detect. It could be an isolated joint, a switch and crossing. It's easy because we know also from the data of the assets, but we can also find, I think there was a question in the chat, we can find bad welded rails, we can find insulated joints, indentations, rail corrugation and squats and everything what was discussed today. The only thing is where we have difficulties is to talk about the amplitude, for example, in the squat, or also to characterize, because some signals are very similar. So at the moment we are not able to characterize it. So say, okay, this is a bad welded joint and this is an indentation that looks similar. And therefore I come to the cons. Yes.
Are you soon? We need to do
yes.
Maybe we could make a transition through what you talk about into the
yes.
discussion.
It's only the slide. I'm ready. I've only three bullet points, and I think then I'm ready. So I think what is it? We have not only advantages from this method. We have also cons. And one is, as I mentioned before, the large amount of data. If you have 20 train running over 10,000 kilometers of track, you have a lot of data. The other thing is also a question in the chat is the localization of the measurement data, especially for high speeds. And if you look for railway surface defects, so you need a very high localization, otherwise you will not find it in a good way. And the last one is that we need special data analytics like pattern recognition or more things to extract the right information and to get more about the amplitudes and the characteristic of this. So this means we need necessary development, and these are driven in future projects such as IM4Rail. Okay, I'm ready.
Yeah, thanks
Thank you
a lot.
very much.
Thanks a
I don't
lot.
know how much minute I talk.
We have 5 minutes, so that's well. I think anyway, many questions are being answered in the chat. If not, we will get all the answers later, and maybe there's a way that that people can also send questions later, and maybe we organize by the end of Intertrack 3 something more for any discussion that people feel needed. But we have to discuss it. I think it's very interesting from Asset Rail side and from DB side. We've seen, for instance, for Asset Rail, positive but also serious concerns and cost impact for the measurements. For DB, I think you also plan ahead, and there are more proven applications already, like in geometry, and there are less proven applications, exactly the ones we work on in IM4Rail and into Track 3. We commenced with them. So also with track stiffness, even maybe more challenging, and RCF. I think we'll get there, but it's a question. I wanted to start with Mart. When you hear the presentations today, you said you had the technique on a hold at this moment, more or less. Do you see maybe something happening here that you say, this is exactly what we're looking for, or this is way ahead, or do you have other suggestions?
What Alfredo said in the beginning, I know that Prorail and the NS, the passenger operator in the Netherlands, are busy to put the axle box accelerators on a lot of passenger trains. That would help if the information is just available for us and frequently available. Instead of that, we have to do numerous of measurement campaigns. So that would be one thing that could help. Yeah, and I think still I haven't heard it, but the depth of the cracks, is a very critical thing. At least for us as a maintenance contractor. So if you go to perform maintenance, you want to make sure that it's gone. If it's still there, it's even going to deteriorate even faster. That's an important thing.
Okay, before we leave the seminar, this is definitely to answer by Rolf or Zili or Alfredo, or maybe you can give an answer. Who can I give the word?
And thanks, and I can say a few words. And currently, the maintenance or infrastructure manager is more, at least what I heard in the Netherlands, is safety driven. And certainly from a safety driven point of view, then the crack depths are very important for decision making. And the thing is that the cracks, when you detect, for instance, by ultrasonic, it is already 4 millimeters deep or even deeper. And in this sense, then it is indeed safety critical, but then it is not good for availability and for economy. So this is why we start from the very beginning to develop something which is for preventive and for predictive. And so then what we are developing, and ABA, our focus has been on the early detection, which once you have found, then you can find a solution by grinding. Even by one path of grinding, that is effective, and it does not affect the track availability because it's one path. So this has been the major drive for this. And for this, then I understand from the maintenance contractor, the strong depends on the policy of the infrastructure manager. So in this sense, then we might have to call for change in the policy of the infrastructure managers, because preventive and predictive is certainly, by definition, better than reactive and corrective. So this is then something then we indeed have to discuss further and to find a better solution for utilization of the technology, which at least in theory has better potential and better for economy and for environment.
I fully agree with you, Sidili, because also maybe it's good for context. The contracts that we do for Prorail are limited to, let's say, 5, 7, 10 years. And the investment that you want to do with the grinding, which is also now responsibility of Prorail itself, yeah, for us too high. But if you look on a far larger scale, yeah, then it will become interesting. So I fully agree with you, Sidili.
Yeah. I think this is an important lesson, yeah, for the rail sector, that of course responsibilities of maintenance are sometimes distributed in the countries, and this technique it gives, yeah, for prediction is intended for prevention of defects, so it should be, yeah, at the benefit of the sector as a whole. It should be organized like that. So that depends from country to country how it's organized. But it's part of the business case and the organization around it. But I think we've seen very promising results today. I don't know if we could extend it for a long while. I think the discussion, maybe we have to say to agree something that we'll be back later this year during Intertrack, maybe final event or some other way where we have possibility for more interaction. We got loads of questions, and we can already take them with us and answer them also later on through Teams or other way. What
Yes.
do you suggest, Mats and Pernilla,
Yes.
maybe also?
Yeah, I'd like to say that there's obviously very much to say about this topic. So we will try and answer the questions in some way. And I think that this chat will be open even after the webinar is over. We can still answer the questions in this chat. And if that doesn't work good, we will try and send out, since we have the email addresses for the attendees, we can also answer questions that way. And also we have our final event in
Yeah,
when
you can
Pernilla?
announce it already. Maybe send the link also on the chat, because I'm not, if there are people outside of Intertrack, they might not know it yet. Yeah.
Absolutely, I will send the link to everyone so they can be invited. It's November 30th, and it will be both online and physical, so anyone can participate.
Yeah.
We will announce the program and with the link and participation link as soon as possible, early next week.
Okay. Yeah. I think for now we have to finish it. The time is over.
Yes.
So it was very compact and lots of information. I think that was really great, and a lot of details for everyone to study, and even better be prepared for the final event, and in between any responses would be good. Yeah. So we're still working on the project, and we still can interact on that. Okay, Mats, do you want to have final?
Yes,
word?
I can wrap it up. So I'd like to thank all the participants for insightful presentation, and of course all the attendees for your participation. Make sure also to follow Intertrack 3 and all the participating organizations on LinkedIn. You find us if you search for us there. And we will have further webinars coming up, also one in October. You find more information. We will give you more information about that later. So yeah, thank you very much everyone for today, and have a great weekend.
Thank you. Bye-bye.
Thank you.
Bye.